introduce Alex Best from one of these mad AI companies, who will be telling us why reinforcement learning needs formal methods.
Yes, thank you very much, Larry. And yeah, the real title is a two-parter. It's why reinforcement learning needs formal methods, and formal methods need reinforcement learning. So I'm going to try and intentionally be a bit provocative and try and convince you of some opinion that I've come to hold, that there's a sort of a mutual dependency between these two. And before we get into that, I'd like to thank the organizers for the invite and for setting this great week up. I've had many interesting conversations already, and I hope to have many more after the talk. And yeah, it's been great to meet so many old friends, but more importantly, I think new people who I haven't had the chance to talk to before. So this has been really great. Thank you. So first, I'll kind of deal with the what is this mad AI lab, as Larry puts it. What is Harmonic? So it's a startup. It's between 1.5 years and 2 years old, and it's really focused on research. It's a commercial AI lab, right? It's focused on building machine learning systems for reasoning, and really doing reasoning via formal mathematics. We really believe that formal mathematics is the way to scale reasoning, and that's kind of what this talk is about. And we're really doing research into how to most effectively bring this about. So that's the approach. And yeah, the goal is to go to at least the expert human level, if not beyond, in formal mathematics and just mathematics and sort of related tasks more generally, right? So we're interested, long term in applications to other scientific domains, to verified software development, all that sort of thing, right? As anyone who's used an interactive theorem prover knows, that there is a big overlap between these two areas, and we definitely see the things that we're developing for mathematics having applications far beyond. So that's the goal. And yeah, everything I'm going to talk about is really due to the entire Harmonic team, in particular also to Aidan Swope, who was due to talk this week but was unable to. And so a big part of this talk is also thanks to his input. So this is by now hopefully uncontroversial in this room. I say hopefully because I think there are likely still some skeptics out there. But this is sort of the baseline that I'm going to start from, and it's the following: machine learning-based tools are useful for developing formal mathematics, and maybe for verified software as well. So from now on, I'm just going to call formal mathematics, verified software, all this sort of thing, formal methods. And if they're not useful for every practitioner today, then they likely will be in the near future. Okay. So what does this look like today? I mean, some people maybe, especially newcomers by now, that they might ask one of these big LLMs like Claude to help them with some Lean 4. They might be using premise selection in like a hammer tool, which is maybe not the kind of the fancy LLM kind of machine learning, but it is or can be machine learning based. And so maybe some of the experts in the room, especially who learned Lean before these tools were really available, or learned any of the other systems for that matter, yeah, maybe they don't use these things, right? And they think they don't need them. And I'd like to try and convince those people that maybe they should. So yeah, maybe the likely in the near future thing is, these tools are kind of coming online, but of course, people really want to play with these things, and some of these things are not yet currently in a form where they can be played with. So that's why I put in the near future. So this is what I want to try and convince you of. It's that reinforcement learning is necessary for the continued growth of formal methods, and that formal methods are necessary for the continued development of useful machine learning for reasoning. Okay, so this is much stronger. I've changed two things here. I've added the sort of contrapositive, right? Well, first of all, I've said that they're necessary, they're not just useful, that we're going to need them. And I've added the contrapositive, right? I've said that you don't just need machine learning for formal methods, but you need formal methods for machine learning, okay? If you want to continue scaling it. So this is what I want to try and convince you. And I've switched here from saying machine learning to saying reinforcement learning. And I'll kind of get to why I've made that change. But it's an intentional one, and I think it's actually key. Okay, so we have heard already in this week quite a lot about these sort of things. So I hope you won't mind me rehashing some of these definitions. I think for some people they're very familiar by now, but I think for others they're still a big jumble of words. So I'm going to try and elaborate on some of these words here. So how hard is formal mathematics? I think it's really hard. I think we forget this sometimes. I think if you've been using these systems for a while, you forget how annoying these things can be. And I think you tend to kind of underestimate the difficulty because you've been through the pain of learning so many lessons the hard way, that it maybe feels a little bit closer than it really is, that formal mathematics will become mainstream, so to speak. So how do we measure the difficulty? I mean, the common thing is to use the Brown factor, right? So this is an old measure. It goes back to the days of automath. It's where you take something like the number of lines in your tech document, and you take the number of lines in your formalization of it, and you divide by one by the other, and you get a number that's like 10. And you say, okay, things got 10 times harder. This has already been mentioned, I think, in Alex's talk. But this is really not what we care about, right? This number of lines is not really the thing which is holding us back, right? It's the human effort, right? If I go away and I start writing some formal development, and then I realize that it was the wrong approach, and I throw it in the bin and I write a new one after filling out half my proofs already, well, those lines are lost, but my effort remains the same, right? So I believe that we shouldn't measure by Brown factor. We should measure by human effort. And what is this number? Well, the Brown factor, right? De Brown says that it's 10 or 20. I posit that the formal effort factor is actually much larger. I think in Emily's talk you mentioned there's this one page of her book with Verity that took, I think, was it 3 months of part-time work to formalize together with Mario, and 6 months to get PR'd into MATLAB. So that, I mean, I don't know how long it took you to write the page of the book, but yeah. So I'm calling this the frown factor, just to be, or maybe defrown factor. But this is just really like the thing we actually want to measure, and it's much harder to measure, right? People, they don't commit their mistakes, right? They don't, record their deleted lines, and they tend not to time themselves while they're working because, well, my assessment is that might be a bit too depressing. So, well, maybe we could have speed running. I guess Kevin would be into speed running, but yeah. So this is kind of the thing that I think is really holding people back, right? Is the human effort. So yeah, in some ways it kind of feels like these formal languages, while incredibly useful, they're kind of closer to the sort of like the low-level languages in terms of regular programming, right? Like there's a lot of things, there's a lot of gotchas, right? There's these strange type errors that you spend 15 minutes debugging, and you can't quite work out why some error isn't applying, and you have to go and kind of inspect and work out why the system is complaining, and that is incredibly difficult for, I think, newcomers especially, but also for experts. So let's continue. How do we scale formal mathematics currently? I think there's been several kind of independent approaches. One is the Kevin Buzzard approach, which is you teach formalization to undergraduates, right? You scale the number of people. And Kevin's been quite open about this being his strategy, and it's been remarkably effective. I think many of the people in this room possibly were undergraduates at Imperial or were somewhere in London and attended one of Kevin's Xena classes, and or somehow they had a second order kind of network effect. Well, we now have many PhD students, right? And junior and senior researchers working purely on formalizing mathematics, right? This is a massive change from maybe even 5 years ago, right? This is an excellent development, and we shouldn't be happy about it, but it's still kind of a human effort, right? And well, we can also kind of go to the wider public. So Terry Tao in his talk mentioned specifically selecting a project that had low prerequisites so that more people would be able to contribute. And I think this is great. I mean, this is a lot of fun, I think, for people who maybe don't have a math background to get involved, but this isn't going to work for every project, right? And I think there is likely also an effect of a big name coming in and drawing in people who might not otherwise have taken notice. So we should be cognizant of that, right? This isn't going to maybe keep working forever. I plotted, I did lean for most of my kind of theorem proving career, so to speak. So most of my examples have kind of come from Lean and MATLAB, but I expect that the things are the same in other systems. So this is a graph showing the number of, did I pick the wrong one? Is this the number of files? Okay, well, the one on the left is the wrong graph. It's the number of files. It should really be the number of lines or something in MATLAB over time. The graphs look broadly similar though. And the one on the right is the number of monthly active contributors. So I did this in a pretty haphazard way. I got an LLM to write the script to do this for me. But I trust this graph broadly, right? Like, this is remarkably similar, the left graph and the right graph, right? Like, the number of lines of code and the number of monthly active contributors is kind of growing broadly similarly, which is a bit surprising. You would think there would be like a derivative in there somewhere, but I guess not. So what's my point here? My point here is that like a lot of the development has been through more people, and that's been great, but maybe we shouldn't rely on that forever. Sorry if I see a lot of people squinting. Sorry if it's a bit small, but if you have questions, just ask. So this is monthly active contributors to MATLAB. So people who made a commit within the last month, and the peak there is about 140 within the last couple of months, which is really cool. The other kind of traditional scaling method is better automation, right? So this is improved specialized automation, right? You can think of tactics that are maybe domain specific, maybe some decidable domain or some domain that kind of has a special structure. Maybe just kind of more generic things, links to automated theorem provers, using ideas that come from SMT solvers and turning them into tactics in your favorite system. These things, I think, they're going to be a massive help. I mean, it's surprising in some ways that the lean community have been without a sledgehammer for so long, and it's incredible that these things are now sort of like on the horizon, right? Or if maybe they're out already. I didn't try it yet, but these things, I mean, I think they'll give us 1 to 2 times, sorry, not 1 to 2, like 2 to 3 times efficiency improvement per person, maybe. Like maybe you'll have to write half as many things as you used to, right? But you'll still have to do the kind of the design work, right? You'll still go down the rabbit hole of setting up your API for your fancy new object wrong and realizing 2 weeks later and kind of going through all that. So these things are still, I would say, inherently interactive, right? They still require looking at the output, diagnosing why they're going wrong, sort of debugging, maybe adding some lemmas, maybe rephrasing to be in a way that's more convenient for one of these tools. And they still kind of have the human in the loop, right? And I think that's sort of fundamentally the thing that I think is going to hold us back, right? Is the human in the loop. So the other thing is the growth of libraries, right? Like as libraries grow, this has been the thing that the MATLAB has kind of taken really seriously, is that as you scale the library, downstream kind of everything becomes a bit easier because all of the easy lemmas are there already, right? Like you no longer have to kind of reinvent the wheel every time. And this is going to reduce this kind of factor of, where you start formalizing something and you realize all the prerequisites are missing. So this is also really, really, really important, but maybe not going to make the difference. So I actually want to go back to the de Bruijn slide, right, and point out something here. And does this red button point? Nice. So on this bottom left, de Bruijn says that the factor is something like 10 or 20, but it is constant. It does not increase as we go further in the book. So this is de Bruijn in the 80s. I forget, they formalized some analysis textbook or something like that. And I guess I would claim that the factor probably does increase as we go deeper into this kind of advanced research level mathematics. So for myself, I know I'm guilty of making proofs in papers that essentially boil down to go look at this other paper and convince yourself that the change I'm making still applies in every argument they make, right? This is not a factor of 10 or 20. This is rather larger, right? And this is one of the things that got me excited about formalization, is the possibility that now you can go copy paste the other paper and change a few things and see what happens. But that's not going to work in every case. So yeah, where were we? So traditional scaling methods are clearly helpful, but I claim that we're still a long way. And if we want formal mathematics to be kind of daily use, the daily driver for mathematicians, we have to dream of bigger things. So the big question that I think you all saw coming is can machine learning help? And I think once again the answer is yes, but there are some caveats, right? I think people who have tried to use these tools in the past have noticed that they've not been that great traditionally at doing formal mathematics. So now I'm going to talk about why the switch from kind of just saying machine learning to saying reinforcement learning. And the key is really this, right? Formal languages are very low resource, by which I mean there's not very many examples of them on the internet, right? The way these machine learning systems, like LLMs, traditionally learn is by taking a bunch of examples, throwing them in, and hoping that they learn something about the language, right? So with formal languages, people measure these things in LLMs in terms of tokens. You can just think of it in terms of characters if you prefer. I estimate, right, once again, rough estimate, don't quote me, but 100 million tokens of, this is Lean specifically, okay? Right, 100 million tokens of Lean on GitHub, right? So if we take all the formal languages, 500 million, right, maybe on the internet. So for Python alone, it is 1,000 times more, okay? So that kind of shows you that, there's 3 orders of magnitude different, right? The way machine learning people do things is like 1 order of magnitude equals 1 thing better, right? So Python is going to be 3 better than Lean, just based on kind of like training on what's on GitHub alone, right? So 3, I don't know, people like to draw these graphs where they have different axes, and it's not really clear like what the intelligent axis really is, right? But you could think maybe 3 years of study better, or something like that, okay? And if you've ever used one of these coding assistants these days, and I would highly recommend people try them, because they are extremely useful now, right? Like I don't know, people in this room are all trying things like this out. But certainly in my job, which does involve a lot of coding in Python, they are incredibly helpful, right? They are remarkably helpful. And this is what I want to get to with Lean, right? Or with any of the other systems. So there's limited training data compared to natural language or to other coding languages, right? So just kind of working on this training data alone in the kind of paradigm that's existed so far is unlikely to yield as good results. The second thing is that what I already mentioned is that generally we kind of save out the result of hours of interactive work, right? And where we minimize things away and we kind of cut off all the vestigial parts and the dead ends and this sort of thing. So in terms of the actual things that end up being saved in a way that might be accessible to someone training an LLM, maybe 1/2 of the work or more is kind of lost by that point. And the other key point here is that this is interactive work, right? So generally, if you're writing, say, traditional software, and you verify the output by running the code and seeing that it kind of does what you want, and then maybe you write some tests, and then maybe you save those tests. And so the thing doing what I want is actually encoded, generally, in some file, right? Tends to be with interactive theorem provers that the thing you're doing along the way to check that the thing makes sense is not persisted anywhere, right? I think Manuel even said earlier that Isabel takes this one step further and completely forgets about the proofs, right? They're not even stored in some object file somewhere that could, in principle, be inspected. Ephemeral. So yeah, some of the information content is clearly lost. And the final thing here I want to point out is that for any individual new thing that we want to do, like say we have our favorite area of harmonics, and we really, really want to start formalizing it, well, there will be 0 examples of that, if we're doing something that's really brand new. And so to hope that something that's trained purely by looking at existing examples will help, it's plausible, but sometimes it can feel a bit far-fetched, right? There's definitely effects of generalization that these large language models have, where they can learn one thing, and then if you give them something broadly similar, they'll be able to work with it. But if you're really doing something quite new, there's no guarantee that you'll be able to make progress with a language model. So reinforcement learning, we've seen this a few times already this week, but they're models, machine learning models that learn from experience, right? They produce some output and they're rewarded, maybe positively, maybe negatively, based on the output they produce, right? So this reward can come from a variety of sources. People try all sorts of different things, but generally it's kind of a system where the system tries something and is graded and updates itself based on that. So why is this really going to be different? Well, this is going to scale with the kind of number of kind of environments it can explore in. So the number of problems. So we don't necessarily need solutions to learn from. We just need problems to have a go at, right? And as long as we have some sort of reward signal, we can keep learning, right? That's, broadly speaking, the big picture here. So there are many more kind of problems possible. Like if I'm a human and I'm sitting down and I'm filling out my Lean file, for example, well, I can make sorries much faster than I can fill them in. That's sort of inherently the problem. So, creating problems to work on is actually, much easier. And they're sort of, maybe right now people don't tend to do this, but like, it is a less intensive work, right? To just sort of create the goals, and let a system go.
That's exactly what I'm doing.
Exactly, yeah. So, just to recap a bit then. These modern language models, they're pre-trained on the internet. So massive text, audio, video data, people throw in Wikipedia, blog posts, articles, books, YouTube videos, captions, anything that they can. And they scale well with the same techniques, kind of the more data you add. That's the kind of beauty of it, right? You add more stuff, things get better. And they learn to predict completions, which means that they tend to memorize factual knowledge, like the 10th president of the United States is, and blah, blah, blah. And you hope that they learn some generalizable reasoning patterns, like breaking down problems into smaller subproblems and this sort of thing. Yeah.
Sorry, but I noticed, but I thought like pre-training had reached a limit, no? Like they were adding more data. Is that true, or?
Yes, that is the very next slide.
Okay, so
Indeed. Yeah, sorry, I kind of skipped over. I kind of made a switch here. I'm going to talk about the converse now, right? So I kind of covered, why. I'm getting very confused by my own title here. Why formal methods needs machine learning, and now I'm switching. I'm going to talk about why machine learning needs formal methods. So we pre-train, and maybe we reach a limit. We'll come to that. And generally, there's a phase of kind of post-training, which kind of draws out desirable behaviors. So you've got this thing, you've trained it on a lot of different data, and it's kind of learned to predict good things as well as bad things. That's, in some sense, the issue, right? Maybe there are some examples online of people writing really bad Python code, and the kind of pre-trained model will predict the really bad Python code just as well as it will the really good one. And so this post-training, you're kind of drawing out the things that you really care about, the desirable attributes, right? So you're going to try and shift the model in some way that it's going to start to only put out good Python code. And the kind of art or science of how you do this, the alchemy maybe, is what all these big labs are doing. So this may include some reinforcement learning-based training, right? So that's a really good way of drawing out desirable behaviors, right? If you have a behavior that you care about that you can associate some reward to, you can draw that out by doing some sort of reinforcement learning training, but kind of still benefit from the stuff at the top. So now we'll come to your point. It's sort of a widely held belief that this pre-training stage has kind of reached diminishing returns. The people have trained massive models now. For example, OpenAI's GPT 4.5, trillions upon trillions of parameters. It takes months and months to train. And it's been widely reported that that was sort of the end of the pre-training era, right? That sort of this continued kind of linear progression, of course when I say linear I really mean exponential, of kind of the orders of magnitude of the training data and the compute is kind of running out, right? Either because there's not enough good data or it's just getting too hard to train these things, but it tends to be that people think that the first is true. So yeah, these previous large model trainings exploit the majority of the data available to them. Of course, one could try and create more somehow, but the internet is already pretty big and it's kind of hard to make a dent compared to that. So what can you do to continue improving these models, right? You can continue to do the thing that would traditionally be called post-training, right? Which is to teach something like reasoning via reinforcement learning, or something that doesn't require a kind of a ground truth known existing answer. But we'll come to that actually. So there are two main approaches here, right? There's, the informal approach. So what's the advantage here is that there's lots of data, right? Like loads of people have asked questions on Stack Exchange and this sort of thing. There's lots of teaching material already out there that teaches people mathematics or reasoning. And the domain is kind of essentially unlimited, right? There's sort of no difference in the informal setting between something that a high school student might do and something that a university lecturer might be researching, right? They're all just kind of words, right? So the quality and correctness in the informal is quite hard to assess, right? So that's the problem I mentioned before. You don't know if a solution is a good solution or a bad solution. It just is, right? And the verification is limited really to things where you already know the answer, right? It's very hard to verify informal reasoning when you don't already know the answer, right? You can either have some other model, try and kind of grade it, but as has been mentioned already this week, like it's not really clear why that will continue working. Like, is verifying someone else's thought process really harder than coming up with your own? And, you can totally imagine that methods like this will stop working so well when the verifier is kind of out of its depth. You have the potential for giving sort of partial progress here, right? You can imagine, because of the kind of the informal nature, you can give partial credit. So, how about the formal side? Yeah, sure.
I mean, there though, the verification, you're saying it's the quality of the verifier. But you've just got the capability to scale the compute and time, right? So in the sense that you could have the same quality of verifier, but just give it longer time and scale that, which people have done. So I'm sort of saying there's a balance to be had between not just the quality of verification, but the compute time you allow it to do.
Yeah, I can definitely see that. I guess I worry that there will be problems that you will get diminishing returns verifying. If your verifier is completely out of its depth, I mean, will scaling compute necessarily help, and how will you know how much to scale it? Yeah, it's not. I think it's
just an extra dimension.
Yeah. No, I think it's as I'll come to on the next slide, people have really deployed this to great success. Right? This is not a bad strategy. I guess the thing that I'm worried about is when these things become near human level, better than expert human level, will we continue to be able to do this? And I guess my feeling is no. So the formal side. Anyway, thanks for the comment, by the way. Yeah. Feel free to interrupt with stuff. By the way, I didn't say that at the start. But, I'm very open to it.
You not got enough material?
I think I do. It's more fun this way. So in the formal side, as we already discussed, there's kind of limited pre-training data. The verification is easier, so to speak. That's the whole point. And it verifies in particular that the reasoning itself is sound, right? You're not just verifying the final answer, and we'll come to this a bit more in a second, but you really verify that each individual reasoning step makes sense, is grounded, is true, is correct, et cetera, et cetera. So, I mean, this is really great. The downside is, of course, that the domain is limited to existing formal developments, right? If I want to go and start training a model with a kind of a formal reasoning component on quasi-groupoid infinitoids or something like that isn't yet in MATLAB, at least last time I checked it wasn't, then I'm going to be kind of stymied, right? There's going to be nothing really to kind of start with. Whereas any sort of mathematical concept that exists, there's at least going to be some kind of informal data about, unless it only exists in Pierre Deligne's head or something like that. We haven't yet managed to work out how to mine that. So yeah, the question really here is, we've got this smaller thing which is better, and this bigger thing which is maybe worse. That's at least what I'm claiming. And can we get the best of both worlds? So that's.
So you're talking about auto-formal. You're not talking about translation. You're really talking about autonomous reasoning.
Yeah. I mean, I think talking about all of the above. Yeah. Anyway, that's something to ponder. So yeah, these recent developments in kind of informal reasoning models. So and I'm sure people have maybe seen by now, but they produce a chain of thought before answering, and it doesn't really resemble human reasoning. I think a lot of these companies out there, they hide this thing, so maybe it's a little bit harder to kind of see it, but it can be quite kind of scattered and incoherent, and it's something closer to kind of trying out many different ideas and kind of ensembling them, right? Sort of taking the average before answering. So it doesn't really correspond, even though it's called chain of thought, to something that we would kind of call human reasoning, which has a much more kind of rigid kind of structure. That's not to say this is a bad thing, but it's just maybe important to note that we have very little kind of introspection into what these things are really doing and how they're getting the results that they are.
Sorry, one more comment about that.
Yeah.
There was the recent Anthropic work where they showed that the chain of reasoning it was saying what the reasoning was did not correspond to what the reasoning was that it was actually doing. And the peculiar thing about that is, of course, they could do it by sort of putting the LLM into like an MRI scan, right? They were actually looking at the level of neurons to do it. What's peculiar, but it's probably the same as humans, it like sort of gives a justification for what it's thought, even if that doesn't correspond to how it got there.
Yes.
So just as a sort of caveat, even if it says...
Yeah, no, I think this is an excellent point. It's really interesting work. I mean, people should definitely look at kind of Anthropic's interpretability work if they're interested. But yeah, they have ways of kind of, seeing what the model is thinking before it really gives its final output. And you can definitely see that the model has already decided what its answer is going to be, and it kind of is actually really coming up with a sort of a post hoc justification. And you know, it's trying to fit the format that it's been trained to, which of course is to produce these long reasoning trains, but that doesn't necessarily mean that the reasoning is really how it arrived at the answer. So that's a sort of the flaw of the approach, a flaw. So yeah, the current kind of reward systems, how do people train these things, right? They train things that get correct numerical answers, right? Or symbolic answers, as we mentioned. So you have a list of math problems which have numerical answers, and you train the model, and if it gets the right numerical answer, then you say, okay, the reasoning must have been maybe not correct, but must have been worthwhile. Okay, so you're kind of relying on the fact that a good reasoning makes you more likely to get the correct answer. But there's nothing really stronger than that that's enforcing. It's sort of a statistical way of enforcing that the reasoning is correct rather than a kind of a factual one. So you can do similar things. You can decide like the truth or the falsehood of a statement. There's been some recent work which, you know, similar to numerical answers, but you know, you can imagine maybe there being quite a lot of bias here. Like I think mathematicians have a pretty good intuition for you know, which statements look like true mathematical statements and which ones look like kind of, you know, it's a kind of a mathematical naturalness that we all kind of know. And we can, I think if I took a, you know, a famous theorem and I negated it and I gave it to you, even if you didn't know the theorem, you'd probably be able to tell which one was the negated one just from the form of the statement, right? You can do similar things for verified software, right? You can make code that compiles be your reward, or running without exceptions be your reward, or code that passes test suites being your reward, right? And so once again, you can do a big chain of thought and output some code, and it can be upweighted if it does one of these things, compiles, passes a test suite, etc. So yeah, what are the problems with these? Well, in the first case, we require like an existing ground truth with an answer, right? If we're going to grade models based on having numerical answers, we need to know the answer. And this creates all sorts of problems, right? First of all, it limits the scope, you know, generally to things with numerical answers, which we'll come to in a second, but is a bit awkward. It introduces the potential for just memorizing the pre-training data, right? If you want something to train something based on having an answer in hand, maybe somewhere from the internet, then probably the model has already seen that in its pre-training, right? So it's not really necessarily testing the right thing. So as we mentioned a couple of times, Epoch AI have this frontier math benchmark that I think they're constantly kind of trying to improve and collaborating with OpenAI to try to improve OpenAI's informal reasoning models, right? This is the O series of models. And so this is Jesper Zhang, who has a math PhD but works in AI, and he wrote his experience on Twitter. So I just posted it here because I thought it was extremely interesting. So yeah, he participated in this symposium with 30 other mathematicians. I think this was also reported in the Scientific American if you want to look at that. And they were asked to create problems which had numerical answers. And indeed, this is tricky, as any mathematician will tell you. Like, it's extremely awkward to take a problem in, you know, homotopy type theory and turn it into something with a numerical answer. And I guess I would contend that there will be always a kind of a bias in the sort of questions that can be turned into a formal numerical answer. So I believe that probably all these people are extremely ingenious and came up with lots of interesting ideas, but there is a clear bias there. And so the other key thing I want to point out here is that the reasoning was occasionally incorrect, and it still managed to arrive at correct numerical answers. So this is something we see. Yeah, there's a question at the back.
About a month ago?
Yeah, this is about a month ago. Yeah.
This is the thing for...
Yes. Yes, this is very recent.
You were at? Yes.
Oh, yeah. Oh, okay, this is great. Yeah, I'd love to. I mean, I think Jasper also said that he didn't agree with some other comments. So I think, you know, even amongst the participants, I think there is, yeah, very different.
One of these things where it's very surprising. Also very mundane.
Yeah. Okay. I'd love to hear more later. Yeah.
What's the new term? AJI or something?
AJI? I don't know.
Artificial jagged intelligence?
Okay, yeah. Artificial jagged intelligence, yes.
I heard people describe it as vibe-based proving.
Yeah, yeah, yeah. So right, this is exactly the sort of thing you can do. I mean, I was talking to Arend earlier, and he pointed out something I'd never thought about, which is that when you're doing informal reasoning, you can assume any widely believed conjecture, right? Like you can assume the ABC conjecture for everything you care about, and you can compute things with floating points and get to something that looks close to an integer and just assume it's an integer. You can compute things modulo a big prime and then just be like, it's probably 7 because it was 7 modulo 1009 or something, right? So there are all these kind of informal tricks you can do that you can basically correctly, almost certainly reason through a problem and get to a right answer without actually doing correct reasoning. And as mathematicians, we care about correct reasoning, and we care about kind of turning this extreme confidence that you might have from one of these approaches into exact correctness. So yeah, the models are encouraged to make educated guesses versus genuine proofs, and this can take the form of knowing a little bit of the kind of the meta strategy, right? Of like, oh, I guess the answer is likely to be this nice 3-digit integer instead of some crazy thing with 5 decimal points, right? Like I think I'm sure the models make use of this sort of approach where you reduce the problem to 2 possible answers, and then one of them looks like a nice number, and you're like, okay, it's probably that one. And so this is about the kind of, well, it's more about the second approach of training coding agents by having them pass tests or produce code that compiles or code that doesn't throw exceptions, is that the rewards are quite hackable, right? Meaning there are ways to kind of achieve the reward that don't really capture the code doing what you want to do, right? So for example, if I'm trying to make my code never throw an exception, I can just catch all exceptions at the top level and return a dummy response in those cases, and now I've got code that never throws an exception, right? If I want to pass a particular test suite and I can see the test suite, then I'm of course going to be able to sort of overfit to that specific test suite. So the rewards are hackable, and models often learn to sort of exploit loopholes, right? Rewriting the tests to be a kind of a less powerful version of the test, for example. Oops.
We saw that, right? We've seen AI writing lean code, but then the test says, yes, that's the proof of the theorem.
Yeah.
But then you look at it, it's clearly not the proof
Yeah.
of the theorem.
Yeah. So I
It's
think
found some trick.
Yeah.
Tricks the verifying.
this is the fundamental thing. Reinforcement learning is going to achieve its reward in the simplest way possible, generally speaking. And so if the reward has holes, it will naturally exploit them.
There's an example with OpenAI where it played chess, and then it changed the rules of chess in the code that it was using to evaluate the chess, which was very scary.
So, I claim, and I think this won't be surprising to anyone in the audience, right? Formal methods are like sort of almost tautologically the solution, right? They are the perfect verifier. They are incredibly versatile. We can encode chess. I think Julian Berman has encoded chess inside of Lean.
He did one pass on.
You can so, you can encode, all sorts of logic puzzles. You can encode, if people have done some sort of physics, some sort of chemical experiments, not experiments, clearly, chemical models. I don't know the status of all those projects, but like clearly the desire is there and the capacity is there to model a lot of different reasoning domains within a formal system. Of course, it might require you to spend a lot of time to come up with the correct axiomatization, but once that is done, you have this sort of unhackable verifier that's very versatile, right? So in that sense, the numerical answer one is also fairly unhackable. Like it has to come up with a answer, and you can check equality. It's the reasoning that's hacked there rather than the result. But formal methods are kind of all of this and more, right? They're incredibly versatile, and they force the models to do genuine reasoning, right? Not to take shortcuts. They of course still can take shortcuts, right? They can still do a preliminary computation that informs the result, the approach, but they're forced to actually prove the thing in the end. Right? So.
The other thing is that what is this number is typically not a question that a research mathematician is trying to answer.
Yes. So, yeah.
It's not only there, it's not the right question.
So yeah, my belief is that, reinforcement learning, for reasoning at least, requires formal methods to continue developing, right? And maybe you're convinced, maybe you're not, but that's where we're at. So I'm going to switch now, after talking about this, it's not really a switch, right? I mean, this sort of philosophy that by training reinforcement learning agents using formal languages is going to get us, expert human level, superhuman reasoning is really the philosophy of Harmonic, not just of me. Great that I ended up working there. And so we're really trying to combine formal methods and RL. And we're also, kind of the slide before, right? Here, we want the best of both worlds, right? We want to make use of things that already exist, right? Informal data. Right? We don't necessarily want to be purists and learn mathematics from scratch for a few reasons. I mean, one is that if you learn mathematics from scratch, I'll come to that in a second. If you learn mathematics from scratch, there's no real guarantee that you're going to learn a sort of a human way of doing mathematics. I guess personally, I feel that mathematics is kind of a social endeavor. Like the things which become fashionable that get worked on, they aren't maybe necessarily platonic. They're a result of people finding things interesting, and that's sort of guided more by human sensibilities than it is by anything that necessarily is a rule of the universe, right? Like which projects get worked on is essentially the choice of humans, right, in research mathematics. And so by yielding completely to formal RL agents that aren't aligned in any way with the sort of mathematics humans find interesting, we're going to kind of lose this connection, right, that we have with the mathematics that we are most interested in. So yeah, we've been designing systems that combine these approaches. Right? So auto-formalization and informal reasoning, they're sort of first-class citizens in our systems, right? So our models sort of, they read and write kind of comments, right? Informal reasoning embedded in formal code. And they include sort of their intermediate thoughts. And so this is sort of more similar maybe to how humans use interactive theorem provers, right? You might write a comment that kind of explains the sketch of the problem you're going to do and then kind of start filling out the stories, right? And so, based on this, they can be prompted to simply solve the problem in a specific way or to follow specific proofs or strategies. So this is indeed auto-formalization, but it's sort of flexible auto-formalization. So, right, we maintain the strong guarantee of correctness of the reasoning. That's the benefit. And we allow ourselves to adapt relatively quickly to new domains by kind of leveraging the informal data. Right? If we have an informal proof in hand, we can try and follow it and try and learn quickly from that, but also maintain the correctness. And as I just mentioned, we're going to kind of remain aligned with the way that humans do formal mathematics or do mathematics. Right? We're not going to go down some rabbit hole. I think the rabbit holes can be very interesting, to be clear. But we believe it's useful to have the possibility of aligning the steps. So the other benefit that we really like is the human interpretability of the outputs, right? There's a potential to kind of easily read and understand and maybe even learn from the proofs produced by the system. So, you've got a long lean proof, and Manuel Heber told me last night that they're right only. And I guess I'm forced to agree with that. Like many of them are kind of difficult to read, even for an expert, without some sort of interactive work. And so, including the informal thoughts allows us to interpret the outputs more easily and to kind of see what the big picture is, the strategy, in addition to the lean detail. And so, by kind of maintaining sort of both of these approaches, you end up with something that's just not brittle. So we can fill in the invisible mathematics when needed. That's the idea, right? So if you have a proof and there's a step which is much harder formally than it is informally, then of course we can still go away and work on it because we have a deep knowledge of sort of the formal side. We're not simply trying to convert word for word informal to formal, but kind of doing them together. So I'm going to show some examples now of kind of what I mean by this. I know I put a bunch of things here, but this is really the philosophy. This is why we believe in this approach, and this is the sort of thing that our systems produce, right? So this is a question in probability, right? It's that the variance, this symbol D means variance here, by the way. I looked it up. Apparently, it's like a Russian term, a convention. But anyway, this is just a random problem, right? Where the variance of the difference of two probability measures is equal to the sum of the variances. And so in here in green, hopefully people can see the colors. I don't know how well they work. We can see the model output includes these comments, right? So first of all, it says expand variance using definition. And there's a nice suffices statement, and we have presumably the formal equivalent of this. The next step, we expand the square and we include cross terms. And we set a 0 because x and y are independent. And so inside of this proof now, we're continuing the proof, and we consider the expectation of the product, and given the independence, we expand it out. Okay? So I'm collapsing some of these subproofs now to make it fit on the page.
Is it generated?
This was all generated by a model. Yeah. This is all the examples I'm going to show. They're outputs of the system. We haven't added or modified these.
How much did it cost and how long did it take?
I'm actually not sure. These aren't, I would say, like particularly crazy output. I picked kind of random examples from our trainings. So I've collapsed some of the subproofs now, kind of to continue the proof, and we can see expanding the square, limited cross terms, right, and we can see the kind of steps, kind of roughly follow what they're meant to. The overall strategy makes sense, and of course we fill in all the kind of the lean steps along the way. So I certainly don't claim that this is. I'm sure someone in this room can probably come up with a 3-line proof of this theorem. That's sort of not the point, right? The point is that the system is working through the problem in a way that is sort of analogous to how a human would, and we're not necessarily trying to find like extremely golfed solutions in all cases. Any questions? Yeah.
Do you provide only the informal text, or do you provide this formalized statement?
I'm not sure in this case. Certainly, the goal is to have systems that go end to end, right? I'm not. Yeah. If I had to guess, I would say this was all coming from the system. In fact, I would put a 90% confidence that all this came from the system. Invisible mathematics, that's a topic that's come up this week, right? Sometimes you try and prove a theorem, and do I only have, sorry, there's 2 clocks at the end. This is very confusing.
Yeah, you have 12 and a half minutes.
I do, okay, great. So we can provide informal proofs, which the system tries to follow. But as we know, when you try and formalize something, quite often you find that there's a gap in the library. And generally that kind of leads to a point where you kind of diverge from the proof you're trying to formalize, because you have to kind of include some auxiliary material on the way. So this is a problem, right? Every positive integer k, there's a sequence of k positive integers, none of which can be represented by sum of 2 squares. And this is a relatively brief informal solution, right? So there's an enumeration of the primes congruent 3 mod 4. Recall there are infinitely many. System of congruences has unique solution. Doesn't really say why. Any number theorist will be able to tell you, but doesn't really say. And some more facts which are probably provable in a few lines, but not completely spelled out, right? It's well known that no such number is a sum of 2 squares, right? This is all of our least favorite words. It's well known. And recall. So this is what the system does in such situations. So we start, following the proof, right? Enumeration of primes congruent to 3 mod 4. Recall there are infinitely many such primes. And now we reach a kind of a point where we diverge. So why do we do this? I mean, at the time, I think this fact is in Mathlib by now. At the time this search ran, it was not. So the model had to come up with the proof, right? So it kind of goes through a few steps here, right? Set of primes congruent to 3 mod 4 is infinite, so we can enumerate them, right? This is kind of the strong form of infiniteness, where you really have a function that gives you all of them. Well, maybe not all of them, but a subset of them. And we do that by actually proving the infinite statement, right? And we do this by following the kind of the proof that a number theorist will tell you, right? You do something kind of like what is proof, but you put a 4 in front or something like that. And so, yeah, let's not go too much into the details, but you can kind of see that we take some time and we solve the subproof. So I'm going to kind of block that out with a ... there, and we continue with the rest of the proof from there, right? So system of congruences with a unique solution, Chinese remainder theorem is the reason this works. So the model's like, okay, Chinese remainder theorem knows that through the pairwise coprime, it does all this kind of stuff, and it continues, right? So let's do that again. And I made the key point, which is the filling in the invisible gaps, but this is kind of the end of the proof now. And when you compress it down by dotting out all the kind of top level halves, you reach something that looks like this, which does look kind of broadly similar to the informal proof. Cool. I will show one more example in a moment, but I guess I want to spend a few minutes thinking about how interaction should look with these systems. I guess, people will have different views on this. Personally, my view is that I want to be out of the loop as much as possible. Right? I want to tell the system what to do and then to trust it to be able to go and execute. Right? I think different people will think differently. Right? And I think that probably depends on what the goals with formalization are. Right? If your goal is really to understand every step of the proof, then you probably want something that's going to be a useful interactive tool, but isn't going to go and do all the fun parts for you. Right? But if you kind of want a completely trustworthy assistant, then maybe you want something more hands-off, right? So I often look at coding agents, tools like GitHub Copilot and whatever Claude Code as kind of inspiration, but I want to know the differences. So maybe on a personal note, I think using GitHub Copilot to write lean code maybe 2 or 3 years ago was the thing that first kind of convinced me that this sort of thing I've shown you on the previous slide is possible, right? That tool had no knowledge of lean, basically. All it could do was see the most recent files you edited, and it could still be occasionally useful 3 years ago, right? It couldn't see the lean state. It couldn't, look up lean definitions unless you happen to have opened the file recently. It couldn't do a lot of the things that you might hope that a genuine coding assistant would be able to do, and yet it was still occasionally useful, right? So this thing that heavily hamstrung was still useful. So that kind of convinced me. So that's kind of an example of the first thing, right? So this is kind of interactive inline text completion, right? So a point I want to make is if you're writing a lean proof, you really need a really good model here. Why? Because you want a model that's going to be able to kind of make good intermediate steps, even partway through a proof, where you can't check whether it closes the goal, right? So this is kind of a bit different, maybe, to something that fills in sorries, where the system kind of autonomously can check its work. So even though this is kind of like maybe basic in the coding sense, the kind of through the lens of verification, this is actually maybe harder than the second thing, right? Which is kind of a full proof completion, right? You write a sorry, even like the demo from Thomas, like you give a sorry, you ask the system to go away and prove it and come back if it found a proof. This is more hands-off, and in some sense can make do with a worse model because it doesn't need to show you anything until it's confirmed that the suggestion is actually good for you, right? So this is, I would say, a little bit flipped, right? It's kind of counterintuitive relative to a coding assistant, where for coding assistants, completing the line of text that you're currently at was sort of like maybe the first stage, and completing full functions was kind of the last stage, right? There's a kind of a strange inversion there. So, well, the next stage might be kind of a partial file completion, right? So maybe you set up, as Kevin does, a file with a bunch of sorries, and you ask some agent to go away and complete as many as possible. And maybe you allow it to add lemmas and do stuff like this. And I think this is the next stage. I mean, personally, this is the sort of thing that gets me really excited, right? It's to specify what I care about, the things that I want to prove, and to have an autonomous system that's really going to go away and do it, making use of the tools that's available. And I guess the final stage, maybe, I don't know if people can think of any stages beyond this, I can't really, is to give in the description, I write file here, but you could think library, you could think whatever. An informal description of what a file should do, you want to produce this complete file, with the proofs, with everything else.
With definitions.
Definitions, yeah. So this is the difference, right? Like here, we're given the spec, which probably includes the definitions. Maybe it's allowed to make auxiliary definitions along the way, but the definitions of the statements you care about are already established. And this is the full kind of hands-off mode. So I don't know if we're going to want anything beyond this, right? Like, you could imagine, right, a system going away and creating its own library from scratch with no, like this automated conjecturing, I guess. But yeah, maybe for now I'm most excited about the last of these. So yeah, Harmonic, we've been thinking a bit about going kind of beyond filling out single proofs and kind of working on kind of setting up files with kind of intermediate theory, and this is an example of that. So here it's another problem, kind of a question kind of style problem rather than a kind of a description of a theory. I have completely messed up the formatting here, I'm very sorry. Hopefully you can work out what it means. But the problem is, given some polynomial, we denote the iterated composition of the polynomial by this, and we have to show that there exists an integer n so that the nth iteration is divisible by 101 for all integers x. Okay. So what does the system start doing? It comes up with kind of useful kind of theory kind of lemmas, right? Like things that you might expect in maybe kind of a MATLAB file, right? So it says that the iteration is kind of periodic, and it says that there exists a kind of a point where it's fixed eventually, kind of proves these results. Then it comes and it does kind of a stronger version of the same thing, where it actually puts a particular bound here instead of an arbitrary n. And then it goes and proves the main theorem. And so I omitted it here for space, but the proof actually uses this version here inside of the proof. So this is kind of like a little taster of like kind of where we want to go, like moving beyond solving proofs and really moving to systems that can, given an informal prompt, create a theory, right, a formalized theory for you. So that's the end of the examples, and I guess I have 2.5 minutes or something, so I'll summarize. So yeah, my belief is that RL is necessary for scaling mathematics. I think we are going to reach a point of human bottlenecks despite the number of really incredibly smart people in this room. And we need some sort of reinforcement learning specifically because of the lack of existing examples, for one, to turn this into a useful tool for a general mathematician, if not the wider public, right? If not engineers, scientists, people who use mathematics. I also believe that, yeah, formal methods are necessary for reliable RL to keep scaling in reasoning domains. Right? Like, I think informal reasoning has made significant progress, but I think it will struggle to go beyond where humans have already kind of written down a lot of the answers. And formal methods are sort of, yeah, they exist, they're really good, right? We should be using them for machine learning. And yeah, this combination will create a kind of a virtuous cycle, right? As we formalize more material, reinforcement learning systems will be able to work on it, they'll be able to improve, and we'll be able to advance formal methods in those areas, which will then lead to further improvements. So I asked one of the LLMs to give me a word that was like symbiosis, but even stronger. And it told me obligate mutualism is the word for two organisms that literally depend on each other for their continued existence. And I have tried to convince you that this is the case for reinforcement learning and formal methods. I don't know if you'll agree with me or if you'll think I'm telling porcupines, but hopefully we can discuss afterwards. I'd like to say thanks to the full Harmonic team, all of our collaborators in the wider community, many of which are here in this room, and sort of people working in formal methods and RL more generally. It's only by talking to each other that we all make progress. So yeah, any questions?
Have less than 1 minute.
Is there any plan to make this tool available?
I don't have immediate plans to share, but I mean, I think of course, like we can't stay submarine mode forever. Yeah.
Oh, no.
Well, I mean, I think the answer is yes, but I can't share like dates. Yeah.
So you specifically said reinforcement learning, but the stuff that you showed, I'm sure you used an LLM there, right? And so
Well,
that's-
you can do reinforcement learning with LLMs.
Yeah, but there's more to it. LLMs are pre-trained in autoregressive, so it's not really RL.
Yeah, I think. I think the boundary is blurry, but I think the point I'm trying to make is that, like, systems that learn from experience and ours do are what's necessary, right? So I think, of course there are like a lot of different things in the mix. Yeah.
Okay, let's thank the speaker again.